Hey everyone, in this video we're going to be doing a little bit more with binomial distributions, and I think you'll find this section maybe a little bit easier than what we did with the probabilities of the binomial distributions in the previous section. So today we're going to be finding the expected number of successes, so that if we have some binomial experiment, how many successes would we expect to encounter, and also we're going to calculate the standard deviation of these binomial distributions. So to give you an example, this could be a very basic type of question that we could ask. So if we have a fair coin, so you pull out a fair coin and you toss it 20 times, how many heads would you expect to flip? Okay, so think about that for a sec, answer that. And hopefully you came up with the right answer. Well, you would expect to flip a head 10 times, right? You might not actually flip a head 10 times. You could get 1, you could get 4, you could get 7, you could get 9. All right, but you would expect if you were to just average, if you just had to guess, right? Some random person said, I'll give you $1 million if you can guess how many heads I'll flip. You might say 10 because, well, you would expect half the time you would get heads, half the time you would get tails. So what you've just done in your head, you've actually just done the expected value or the mean of a binomial distribution. So let's think about how you arrived at this conclusion, right? So you threw it 20 times, all right? So that would be sort of your n, right? Your n was 20, total number of flips. And then let's think about if there was another variable maybe that you used. So you used the fact, most likely in your head, I'm guessing, the fact that you would expect 50% or 0.5 or a half, right? That's the probability of getting ahead. So that's like your P, right? P is 1/2 or 0.5 or 50%, however you viewed that. That was your P, your probability of success, right? Probability of success. Okay, so then what you did to come up with this 10 is you did your mean or expected value. I'm going to call that this U thing here, which we called mu. You did 20 times a half or 20 times 0.5, and you got 10, right? That's what you did in your head. Okay, so that is actually the formula here. Mu equals, well, we did n times p. That's the formula for the mean or the expected value. And again, you did that in your head without even thinking about it. There you go. So our first formula, the mean or the expected number of successes, is simply mu, okay, that's our symbol for mean, equals NP. That's it, mu equals NP, okay? Where N equals the total number of trials, and P, same thing as it was in the last section, is the probability of success. Told you it was easy, right? Total number of trials times the probability of success. That gives you your expected outcomes. Okay. And then another thing which we often do, standard deviation, that that measures sort of how spread out the data is or the variation within it. Pretty simple formula for that one as well. The symbol that we use is the sigma here. It's kind of like an O with a little tail on top of it. And that is the square root of NPQ. That's it, square root of NPQ, where N is still the same thing. N equals total number of trials. P represents the probability of success. And Q, as the same as the last section, represents the probability of failure. Okay. So in that coin flip problem, if the mean was, well, oops, just trying to change colors here real quick. It'll let me. All right, there we go. If the mean, mu, was NP, so that was 20 times 0.5, give us 10. We expect 10 heads, for example. Well, the standard deviation, our example, would be sigma equals the square root of n, which was 20, times 0.5 is our P. And think about what the Q would be. Remember, Q is the same thing as 1 minus P, right? It's everything that's left over. If there's a 50% chance of success getting ahead, there's a 50% of failure, which indicates getting a tails. So 20 times 0.5 times 0.5 in the square root. And you can just type that in your calculator, all in one square root there. Just do square root 20 times 0.5 times 0.5. And we get 2.23. Or 2.24, we'll round it up there. 2.24. So we expect to get 10 heads with a standard deviation of 2.24. And that's all there is to it in this section. We're going to be looking at some example problems. Sometimes the hardest part is interpreting the problems to pick out what the N, the P, and the Q is. So I would recommend on all of these going through first thing, find N, P, and Q, and then try to answer the question. All right, so let's say we have a college entrance exam and only 10 students on average qualify. 90% are not admitted to the program. So maybe like trying to get into like a law school or just a competitive nursing program or something at a school. Only 10% of the students normally qualify and 90% are not expected to qualify. So you've got a group of 30 students. They're all going to appear to take the test. And the question is, how many would you expect to qualify? Okay. And in the course of this, answering this question, we're going to calculate the mean, and then I also want to calculate the standard deviation. So the first thing that we're going to do is find N, P, and Q. So N represents the total number. Well, let's say we had a group of 30 students, so that's going to be N equals 30. P, the probability of success. Well, a success, think about what a success is in this case. How many expect to qualify? So qualifying is a success, right? It is important that you identify what is measured as a success in this case. Because remember, a binomial experiment is an experiment where there's either success or failure. There's only two options, succeed or you don't succeed. So qualifying is a success. 10% qualify, so that's going to be 0.10. All right, and then failure would be everything that's left over, so 1 minus that, which would be 0.90, which it also says 90% are not admitted to 90% fail. So with that, we can answer these two questions. How many would you expect to qualify? So that's going to be the mean, just going to be NP. So we do 30 times 0.10. Pretty simple. And that's just going to be, 3. So we would expect 3 to qualify. That's our mean. Our standard deviation, sigma, is square root of NPQ. So 30 times 0.10 times 0.90. Let's type that all in. And that gives us 1.64. There is more that we could do with that standard deviation. For the time being, don't worry about really, obviously if a standard deviation was super high, then that means you might have done it wrong. But for now, we're not going to worry too much about the standard deviation. But a different application that you could do with this is if you were to figure out outliers, you would use the standard deviation. If you remember from past chapters, an outlier would be something considered outside of 2.5 standard deviations of the mean. So what we've done in the past is, and this is for outliers. You're not going to be asked to do this on the assignment, but just to show you why this would be helpful. Outliers are, remember, mu plus or minus 2.5 times the standard deviation. So for instance, let's just do the over. 3 plus 2.5 times 1.64. So let's say 3 plus, let me go ahead and do that real quick. 7.1. So anything outside, so if more than 7.1 students passed, that would be unusual. So the reason this would be helpful is, let's say you had a group and 10 students passed, right? That would be very rare. So maybe you even start to suspect, well, did those students cheat? Did they have inside information? Or was it just a really good group of students who were extra smart? but statistics can help you identify, in this case, an instance of cheating possibly, right? Or if maybe none of the students qualified, or just certain amount, right? You could say, well, maybe this test is too hard. It's not enough for qualifying. So at any rate, that's how we could use standard deviation. For the purposes of this assignment, you just have to do those two things. All right, let's go and look at the next one. So let's say on your first semester stats exam, there were 8 multiple choice questions and you had no idea how to solve them, right? Each of these questions has 5 answers and you randomly guess on each one. How many would you expect to get correctly? So you're trying to think, well, how many am I gonna, I know I got all the other ones right, but how many am I actually gonna get of these 8 correct? So we do need to pick out the N, the P, and the Q. So N represents the total number, which is 8 multiple choice questions. Total number of trials. P, a little bit more challenging on this one. Probability of success. Well, it says there's 5 answer choices. So that means the probability of you being successful is only 1 out of 5, because you only got 1 out of 5 chance of getting the right answer. So success is, obviously in this case, a right answer. That's a success. You only got a 1 out of 5 chance of getting the right answer. So 1 out of 5. If you want to go ahead and make that decimal, you could as well, 0.2, or you could just leave it as 1 out of 5. Which means the probability of failure would then be 4 out of 5. You got a 4 out of 5 chance of getting the answer wrong, which is equivalent to 0.8. Okay, so now we can answer how many we would expect to get correct by getting the mean. So that's just N times P, so 8 times 0.2. And that's just 1.6. So you might round this up since it's 0.6, so approximately 2 correct. That's about how many you would expect to get correct, between 1 and 2. And then for standard deviation, sigma, it's going to be the square root of NPQ, so 8 times 0.2 times 0.8. Going to do that. Again, just type that all in one line in your calculator. We get 1.13. And that's it. Go ahead and try 2 more. All right, in this one, a hospital, there is a deadly disease. This may be actually, I guess you could think about with COVID. This question I actually wrote last year, but maybe is even more appropriate with COVID now. So let's say, could even modify this question. Let's say in a hospital, 60% of patients over a certain age with COVID are dying with COVID when they get admitted, something like that. On a certain day, 15 patients get admitted to the hospital with this disease, COVID. How many patients would you expect to survive? So how many are going to live? We're going to calculate the mean and the standard deviation, and that will allow us to answer this question. All right, so we can try to pick out the N, the P, and the Q. The N is the total number of trials, or in this case, the total number of patients. So that would be 15 patients, right? Total number on a given day. The P, the probability of success. Okay, so this one's maybe a little bit more challenging. It says 60% are dying, right? Not really the greatest thing to think about. However, we're going to ask, how many would you expect to survive? Okay, so we're going to take a little bit brighter outlook on this. How many would you expect to survive of this disease? So what is the probability of surviving? Because our success is surviving, right? What is that probability of success? Well, if it's 60% are not surviving, 40% or 0.4 would be probability of success, right? Because our success is not dying, obviously, right? Success is surviving. So if 60% are dying, then 40% are surviving. So then our probability of failure, which in this case is dying, right? So this is surviving, would be 0.60 or 60%, because that would be dying. Right? So from here, let's go ahead and calculate the mean and the standard deviation. The mean is NP, so 15 times 0.40, and that is going to be 6. So we would expect 6 of those patients to survive. And then the standard deviation, NPQ, 15 times 0.4 times 0.6. Second square root of 15 times 0.4 times 0.6. 1.89, actually about 1.9 if we round that up. Okay. All right. So in this particular question, let's try to apply this to real life. And it's not maybe the best thing to think about right now. And this question last year when I did this wasn't as meaningful or maybe hits home as quite as much as this question does today. But let's say you've got a particular hospital and they're doing some sort of treatment. Like, I don't know if you remember back in the beginning of COVID, things like they were suggesting like hydroxychloroquine or vitamin D, different drug combinations were helping people survive. So let's say on average, they were only expecting 6 out of 15 patients to survive. But let's say a particular hospital has, 10 or 12 out of every 15 patients survive. And so we could determine if that was an outlier, like, if it was unusual, right? And if it was beyond what we would expect. So if it's beyond more than 2 standard deviations, so let's say our mean plus 2.5 times 1.9, right? So let's say a particular hospital, let's go into this calculations real quick. So we would expect the range to be no more than 10.75, so approximately 11. So let's say we had a particular hospital and they had 12 out of every 15 patients survive. Well, that indicates that maybe they're doing some sort of treatment that is positively impacting beyond just the margin of error. So maybe we would want to do more research into what is that particular hospital doing that's allowing their patients to survive at an extraordinary rate beyond the margin of error. And then we could look into their treatment and then maybe do some tests to see if their treatment is particularly effective. Let's go ahead and look at our last question. We've got a particular set of parents, and there's a 25% chance that the children of those parents will have a blood type of O. So these parents are then going to have 7 children. And the question is, how many would you expect to have blood type O? Well, let's go ahead and do our N, our P, and our Q. So N is the total number. In this case, it's going to be children. We have 7 children. And let's think about what a success is determined in this. So expecting an O blood type. So O blood type would be a success, having an O blood type. I think O is, one of the O's is universal donor, maybe. I think I'm O positive, which it's I think it's the universal donor. So that would be a good thing, right? More universal donors. So what's the, how many would we expect a success or having the blood type of O? So that is going to be a 25% chance of having blood type of O. So that's going to be 0.25. And then our probability of failure is going to be 0.75. 1 minus 0.25, 0.75. So then our mean, N times P, 7 times 0.25. And that's going to give us 1.75. So let's go and round that up to 2. So approximately 2 children with a standard deviation, sigma of square root of NPQ, 7 times 0.25 times 0.75. Equals 1.15 approximately. All right, so that is all there is to it, guys. Just those 2 calculations on all the problems, making sure you correctly identify the N, the P, and the Q, first of all. And if you do have questions interpreting any of the problems, make sure that you do reach out to me. All right, see ya.